So when you blink your eyes, the muscles in your face contract, right?
Yeah, they do.
And that creates an electrical spike so massive that it completely drowns out your actual brainwave.
Oh, completely. It's a huge surge.
Right. So if you are hooked up to a brain-computer interface, that simple, biological human blink looks like a catastrophic system error on the monitor.
It's basically a red alert for the hardware.
Exactly. You are left trying to pull this really delicate, high-frequency human thought out of what is essentially an absolute biological thunderstorm.
And, the real bottleneck in neuroengineering, it hasn't actually been the physical hardware for a long time.
Oh, really?
Yeah, I mean, anyone following the BCI space knows that modern EEG caps and Arduino sensors are incredibly sensitive now. We can capture the signal just fine.
So what's the holdup?
The actual wall we hit is the ingestion architecture. Like, how do you process that thunderstorm of biological data in real time without completely losing the underlying cognitive signal?
Well, that is the exact problem we are tackling in today's deep dive. We've got our hands on a really comprehensive system architecture diagram and a detailed research proposal for the Brain Systems Telemetry Lab.
This is the one spearheaded by Vinicios Ongaratto out of the UK, right?
That's the one. And this blueprint, it doesn't just theorize about reading minds. It maps out the actual functional, heavily engineered data pipeline required to make it a reality.
Which is so refreshing to see.
It is. We are going to trace the exact journey of a human thought, starting from, a messy, raw biological voltage, all the way to a clean, searchable piece of digital knowledge.
Knowledge that's actually capable of controlling next-generation hardware.
Exactly. Because before you can even think about commanding a computer with your mind, you have to capture and translate the thought without the system crashing every time you, blink or your heart beats.
Right, and that requires an incredibly robust ingestion engine at the very front of your pipeline.
Okay, let's unpack this. Before any downstream data processing can happen, we have to actually ingest that raw biological voltage. The architecture designates this application called Brain Reader as the primary motor for this initial phase. The documentation notes that Brain Reader is built on FastAPI, and its core responsibility is to grab that raw sensor data and output what the system classifies as, quote, unprocessed telemetry.
Yeah, and think about the physics of what Brain Reader is actually handling here. A raw EEG signal is just this continuous, totally chaotic stream of fluctuating voltages.
Just a mess of data.
Exactly. You have alpha waves, beta waves, and theta waves, and they're all overlapping, and they're mixed with the ambient electrical noise of the room.
Even the room noise.
Yeah. Plus the patient's pulse, and of course those massive muscle spikes we mentioned from blinking. So Brain Reader takes that continuous analog wave and converts it into discrete signal amplitudes. It translates a physical voltage into a structured digital state, basically attempting to identify whether the brain is engaging in cognitive activity or if it is just in a resting state.
So if it is just recording fluctuating voltages, that seems, relatively straightforward. But the proposal specifically mentions that Brain Reader features an optional AI layer right at the point of ingestion.
Right, that's a key detail.
Yeah, that implies it isn't just a passive microphone recording the noise of the brain. It must be actively interpreting and structuring the data before it even hits the primary database.
Exactly.
I mean, that is a massive computational load to place on the very front end of an architecture.
It is a heavy processing load, but it's a strictly necessary one. Because if you wait to structure your data until after it has been stored in your database,
you just get a huge backlog.
Exactly. You immediately create a massive backlog of raw, totally unusable telemetry. So by placing an AI layer directly at the ingestion point, Brain Reader instantly transcribes the biological shouting into a standardized format.
We need a solid way to visualize this mechanism. Let's look at it like trying to isolate a specific instrument in a symphony.
I like that.
So the brain is playing every single instrument at maximum volume all at once. Brain Reader isn't just hitting record on the whole orchestra, it's acting as a dynamic acoustic filter. It actively listens to that chaotic sound wall, identifies the specific frequency of, say, the cello, which represents the cognitive state we actually want, and it transcribes only those notes into sheet music instantly.
That captures the active nature of the ingestion perfectly. It is isolating the frequency of interest and structuring it right then and there.
And that's why they use FastAPI.
Right. FastAPI is specifically chosen for this because it handles asynchronous data streams incredibly well, meaning it can process these high-speed biological inputs without lagging.
Makes sense.
But even with that sophisticated front-end transcription, the output moving into layer 2 is still classified as unprocessed telemetry. It has been captured and formatted, but it hasn't been rigorously cleaned.
Which means we collide with the reality of biological artifacts.
Yeah, the messy stuff.
So the architecture moves the telemetry into a transformation pipeline using a tool called DBT, or Data Build Tool. And the visual source explicitly highlights a critical step here called overcoming signal artifacts.
Right.
This is where the unprocessed data is processed into clean tables and then finally into model-ready data sets.
So artifact removal is where pure data science intersects with neurobiology. An artifact is literally any signal in the data that isn't the targeted brain activity.
Like the blink.
Exactly. We discussed the eye blink earlier.
Yeah.
Biologically, a blink generates a massive low-frequency wave. But a conscious thought, like deciding to move your hand or, solving a math problem, that happens at a much higher frequency, but with a significantly lower amplitude.
So the blink completely dwarfs the thought in the data feed.
It totally buries it, yeah.
So the DBT pipeline applies specific algorithmic filters to isolate that massive low-frequency blink and subtract it, while preserving the delicate high-frequency cognitive data sitting right underneath it.
That's the goal.
That sounds mathematically perilous. I mean, if we scrub the biological data this aggressively just to generate a uniform model-ready data set, do we risk losing the actual nuance of human thought?
It's a valid concern.
Are we just over-sanitizing the data to the point where we accidentally erase the very cognitive signal we're trying to study?
This raises an important question, and it actually sits at the absolute core of neuroengineering debates right now. The risk of overfiltering is precisely why Ongaratto's architecture relies on DBT.
How does DBT help with that?
Because this layer isn't just about scrubbing the data, it is fundamentally about traceability.
Okay, traceability.
Right. In a traditional, less rigorous setup, a researcher might run a custom Python script that subtracts the blink. But they are left with a new, supposedly clean data set without any permanent record of exactly what mathematical operations were applied to get there.
Oh, so you end up with a complete black box. You possess this pristine brainwave, but you have literally no way to prove to another scientist or a peer-reviewed journal that you didn't accidentally delete critical cognitive data during your scrubbing process.
That is exactly the problem. In serious scientific research, trust requires documentation. The DBT platform structures, standardizes, and documents the entire lineage of the data.
So it tracks everything.
Every single transformation. If an algorithm identifies a heartbeat frequency and removes it, DBT logs the exact parameters of that filter. You can trace the final model-ready dataset all the way back up the chain to the raw, unprocessed telemetry.
That unbroken chain of custody is what makes the outputs mathematically trustworthy.
Yeah, exactly.
You aren't just presenting a clean signal, you're presenting the entire verifiable history of how that signal was refined.
And that rigorous documentation process is what allows the Brain Systems Telemetry Lab to achieve multidisciplinary integration. They're basically proving to data scientists that the neurobiology is sound, and proving to neurobiologists that the data science is sound.
Okay, so we have this unbroken chain of custody, and the data is pristine. But all of this rigorous back-end processing creates a completely new logistical problem.
Oh, absolutely.
How does a human researcher actually keep track of it all? If the system is constantly filtering out blinks and heartbeats and logging every single transformation, the sheer volume of metadata would just be unreadable for a human being.
Right. An automated system of this scale is completely useless if the human operator cannot steer it or understand what it is doing in real time.
The human has to remain the conductor of the experiment.
Exactly. And that brings us to the interaction and control layer of the architecture.
The blueprint details the SLRPD project, which serves as the foundation for both agent synchronization and portal access. Now, SLRPD isn't churning massive volumes of data like Brain Reader, right?
Oh, it's totally different.
Rather, it provides the actual user interface for parameter manipulation and data entry. And here's where it gets really interesting.
Yeah, this part is amazing.
The documentation states that SLRPD orchestrates intelligent agents to actually explain experiment events back to the user.
We are seeing a massive paradigm shift in human-computer interaction, or HCI, within this framework. Historically, a scientist would monitor an active BCI experiment by, staring at a dashboard of raw line graphs.
Just staring at squiggles on a screen.
Or digging through thousands of lines of dense log files to figure out why an anomaly occurred during a session.
So if a sudden massive spike occurs in the data stream, the scientist usually has to pause the experiment, pull up the logs, and manually trace the pipeline to see if the spike was a genuine cognitive event or just a muscle twitch.
Exactly, which takes forever.
But SLRPD replaces that manual forensic digging with an active AI lab assistant. It monitors the data flow, recognizes the anomaly, checks the DBT pipeline lineage, and can essentially tell the researcher in natural language, hey, we registered a massive amplitude spike at 2.04 p.m., but the pipeline correctly flagged it as a cardiac artifact and isolated it.
The operational efficiency gain there is just incredible.
Right.
It allows researchers to test data flows and validate system behaviors on the fly without breaking their concentration or halting the experiment.
That's huge.
When you architect systems with this level of complexity, the HCI layer is just as critical as the underlying signal engineering. SLRPD ensures that no matter how much automated data modeling is executing in the background, the researcher maintains total situational awareness.
Okay, let's recap where we are. So, Brain Reader acquires the raw signal. The DBT pipeline rigorously cleans and documents it. SLRPD allows the human to monitor and orchestrate the entire flow via intelligent agents.
Right.
Up to this point, we are talking about an incredibly sophisticated, highly optimized data processing pipeline. But the architectural blueprint outlines a phase 1 evolution that completely shifts the capabilities of the lab. It introduces layer 5, semantic indexing.
Yeah, and this specific layer is where the architecture transitions from, because it's a passive storage system, into an active associative network. Ongaratto's blueprint plans to take these perfectly clean data sets and run them through vector databases, specifically utilizing a technology called Weaviate.
So the pipeline transforms the semantic data into vector embeddings, which then output as searchable knowledge. The sources explicitly call this giving the system a vector-based semantic memory.
Which is a brilliant way to phrase it.
To really grasp the gravity of this evolution, we have to look at how vector databases fundamentally alter the concept of searching. Normally, if you query a standard database, you are looking for an exact character match.
Right.
You search for a specific patient ID, a precise timestamp, or a defined numerical parameter.
Because a traditional relational database only understands the exact string of text or the specific numerical value you input. It has absolutely zero comprehension of what the data actually represents in the real world.
But vector embeddings map data in a multidimensional space based on its underlying characteristics.
Yeah.
Think of it like mapping a massive city using complex longitude and latitude coordinates. Instead of searching for an exact street address, you are searching by location and proximity.
Exactly.
Concepts that share similar meanings or characteristics end up living in the exact same neighborhood in this multidimensional space.
And what's fascinating here is how that mathematical mapping applies directly to human thought. By converting biological brain telemetry into vector embeddings, the system stops looking at raw numbers and starts looking at the fundamental geometry of the data.
Yeah, the geometry of thought.
Yeah, it maps the mathematical relationships between different cognitive states.
So it isn't just checking if voltage A equals voltage B. If I'm understanding this mechanism correctly, it is mapping the geometry of the entire neural state. That means you could theoretically query the telemetry portal not for a timestamp, but for an abstract concept. You could ask it to show you the neural pattern of someone experiencing a sudden realization.
And the system would instantly search its semantic memory for that specific geometric shape. It can compare neural patterns across entirely different clinical sessions or even across entirely different patients.
Wait, really? Even with different people?
Yeah, because it recognizes that the fundamental shape of the data for a sudden realization lives in a specific neighborhood in that multidimensional space.
Yeah.
Even if the raw baseline brainwave amplitudes of the two patients were completely different.
Wow. It functions as an associative thinker. It actually understands the context and the meaning of the telemetry, not just the raw electrical output.
It does.
That pushes this entire lab from being a tool that merely records the brain into a system that actually understands the underlying patterns of human cognition.
It creates a true semantic memory of brain states, which is an unprecedented resource for neuroengineering.
Reading through all this, the integration of fast API ingestion engines, DBT traceability pipelines, AI agent orchestration, and Weaviate vector databases, it sounds like highly theoretical computer science.
It really does.
It feels like a roadmap for a futuristic research lab conceptualized for the year 2050. But the sources emphasize heavily that the foundation of this architecture is grounded in real-world deployment today.
The integration and continuous deployment are already active. Ongaratto's blueprint notes that the core components, Brain Reader, the DBT transformations, the SLRPD interaction layer, they are continuously deployed using a cloud platform called Render.
So it's real.
This isn't speculative software waiting for funding. It is actively running code functioning in a real environment right now.
Having that foundation poured, tested, and functionally deployed makes the ultimate goals of this research much more immediate. Because the proposal explicitly details plans to push this architecture far beyond basic academic research.
Oh yeah, they are thinking way bigger.
The stated target is to integrate these semantic brain-computer interfaces with advanced computational models and specifically hypersonic robots.
I know, moving from analyzing clinical EEG data in a lab to interfacing with hypersonic robotics seems like an extreme leap, but it is actually the logical endpoint of building an architecture entirely focused on absolute data trust.
It is a staggering contrast in application. I mean, we started this discussion talking about the struggles of filtering a simple heartbeat out of an electrical signal, and now the blueprint is proposing telemetric control over hardware moving at Mach speeds.
If we connect this to the bigger picture, the reason they can even propose hypersonic integration is because of the grueling data engineering established in the early layers. Think about the stakes of physical actuation latency.
Okay.
If you're using a brain-computer interface to control a motorized wheelchair and a muscle twitch causes a false positive command, the chair might jerk forward an inch.
Right. It is an error, but it's manageable and physically safe.
Exactly. But if you are interfacing with a hypersonic aerodynamic system, a false positive isn't just an error, it is catastrophic.
Right. If the system misinterprets a patient's eye blink or a moment of resting state as a definitive command to bank left at Mach 5.
The physical hardware tears itself apart under the G-forces.
Wow. Which is exactly why you cannot integrate human brain telemetry with high-stakes physical systems until you completely solve the muddy biological signal.
You'd have to solve it perfectly.
The rigorous asynchronous ingestion by Brain Reader, the uncompromising artifact removal and data lineage tracked by DBT, the real-time agent monitoring via SLRPD, that entire gauntlet of validation is the absolute prerequisite for safety.
You cannot safely fly the advanced hardware with your mind until you can mathematically prove, beyond a shadow of a doubt, that you have isolated the intentional thought from the involuntary blink.
The heavy, meticulous data engineering of today is the only thing that unlocks the high-speed physical applications of tomorrow.
They are building the trust layer first.
Well, we have traced the complete functional journey engineered by the Brain Systems Telemetry Lab. We have seen how Vinicios Ongaratto's architecture acquires a chaotic biological signal using the FASTA-PI-based Brain Reader, how it relentlessly cleans and documents it through DBT pipelines, and allows human researchers to orchestrate the flow via AI assistance in the SLRPD layer.
Yeah.
And we've seen how Weaviate vector databases give that data a semantic memory, allowing computers to search our neural patterns by their actual meaning, all laying the groundwork to safely interface with hypersonic technology.
It truly is a masterclass in pipeline architecture.
Yeah.
They aren't just reading the brain. They are translating raw human biology into a verifiable, trusted digital standard, layer by rigorous layer.
This deep dive gives you the shortcut to understanding the actual functional mechanics driving modern neuroengineering. It is not science fiction magic. It is rigorous signal processing, verifiable data lineage, and semantic indexing.
Good, better.
But before we let you go, I want to leave you with one final thought to ponder, building on this concept of vectorizing human thought.
The philosophical implications of mapping the brain geometrically are incredibly profound.
If this system can map, vectorize, and search our neural patterns by their underlying meaning, what happens when we start comparing the vector embeddings of different people experiencing the exact same emotion?
Oh, that's a wild thought.
If we look at the clean telemetry of joy or grief, or a sudden realization across thousands of different minds from vastly different cultures and spoken languages, could an architecture like this eventually prove that human consciousness itself shares an identical, searchable mathematical structure? We'll let you mull that over. Until next time.